In this video, I'm going to look at Mathematica slash Wolfram-Cloud. I'm going to look at, get some random numbers from a distribution and look at sort of some variations on histograms, sort of different arguments in the histogram function in Wolfram-Cloud. So the first thing I'm going to do, I'm going to be mainly here working with a normal distribution. So I have here the normal distribution, and it has two arguments. And the first is the mean, the average, and the second one, the standard deviation. And I'm going to use the sort of standardized normal distribution. So a mean of 0 and a standard deviation of 1. And then with that distribution, I'm going to pull independent random variables from that distribution. And here I'm grabbing 500 of them, and I'm calling it that my sample 500. And here's some answers I got previously. It's random, so it's going to give me different answers this time. And I'm doing a shift enter. And it's giving me this list of all of these values drawn from that distribution. And there, as I say, my sample 500 is 500 of them. And I'm going to do the same thing, but grab 1,000 of them. So my sample is 1,000, my sample 500 is 500 of them. And 1,000 takes a little while to generate them, but there they are. Okay. Okay, now I'd like to make histograms and see sort of like there are some variations on histograms. So first I'm just going to make a basic histogram, and I'm making a histogram of from my 500 sample, and the values are going to change, but it's mostly going to look like what I have here. And chart style of just giving it some colors. This is some sort of a range of pastel colors. Shift enter. Okay. So there we have. So one of the options is to give it some styling. Otherwise, I think it has some default color and makes all the columns that color. Or we'll be able to choose the color, as we'll see in a minute. But that's sort of one of the options. Not one of the more important options, but it's nice to make things look interesting. Okay. I'm going to make another histogram. That histogram was of the 500 sample. And in a histogram, you're finding out the frequency, the number of times something occurred. So I got values sort of going up to 0, maybe between a half and a minus 1/2 and 0, about 100 of them. And over here between 0 and positive 1/2, I got about 94 of those. Some fluctuation as you expect when you're getting random variables. Okay. I'm going to make another histogram, this time of my sample. So that's 1,000. I'm going to make it light blue. And this one I'm going to give a title, a plot label. So just showing you little things you can do. You can title your histograms. You can label axes if you want. What I'm just pulling is numbers, so it doesn't it's understood that for a normal histogram that the y-axis is the frequency, so I don't necessarily see any reason to name it. And I'm just pulling something from an abstract math distribution, the normal distribution. So there's no real label or units for my x-axis here either, but I can label them if I want. But again, just sort of making another histogram. And I haven't been naming these histograms just so that it's easy then to I want to put them together. So I'm showing H and H500. So 500 was the histogram when there were 500 samples. H was the 1,000. And the order here matters. So let's do it Shift Enter. And there we have the two. And if I had reversed the order, you'd only sort of see the bigger one, and the littler one would be sort of hiding behind it. So the order matters. But we see here, and this makes sense, when there were 1,000 samples, then this between -1/2 and 0 came up about 208 times, or down here for the 500 sample, it came about 100. So one thing I just want to show is that the height is dependent, as you expect, on the number of samples. Now, one of the built-in ways that Wolfram has of making histograms sort of will eliminate this dependence on the sample size. And so that's one of the things I want to show here. Okay. Now, but before that, I want to show one of, so there are these named things like the chart style, which gives me the coloring, and the plot label, which sort of gives me this title. But if you have a sort of an unnamed second argument in the histogram, they're calling it the B spec, or the spec for the bin. So the bin is these sort of groupings of numbers. So I have numbers, sort of numbers from the line, sort of any real numbers, and then they get, when you make a histogram, they get sort of binned up, all the numbers that fall in a particular range. And here, the B spec allows you to have some control. Now, I don't quite know here what they mean by 10. So I have this second parameter. And the second parameter, there are variations on this bin spec parameter, and one of them is just a number. So, my mind says is that I want it to be the count, but it's not quite the count, because here there's a little one here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's sort of like 14 of them, and when I specified 10, so it's not the number of bins. It's related to the number of bins, but it's not exactly the number of bins. So you'd have to dig further into their documentation to figure out exactly what it is. But it does control the number of bins, but the count is not exactly the number of bins. Okay. But so there's this integer value B spec, which was 10. I'm going to do it again. I did enter that one. Yes, I did enter that one. I am going to enter it again, but this time making it 20. So I'm going to have more bins, so they will be smaller. Okay. And so I have smaller bins, and then I want to show them again together for this comparison's sake. And so I had a B spec of 10, then a B spec of 20. And here is here's the result. So I'm getting, seems to be about sort of 2.5 of the green to 1 of the pinks. Okay, so there's that. And also the height comes down, because the height is related to how many times you fell in a certain bin. Well, if the bins are smaller, you're less likely, or it's going to be less often that you fall into that bin. If the bin's smaller, you're going to fall into the bin. And so the heights, the green heights, are shorter than these pink heights. That makes sense. Okay. Here is a different version of B spec. And they have about 4 or 5. I'm going to show you, I think, 3 of them. And this one has a list with 3 things in it. Where I want to start making my bins, sort of a minimum, where I want to stop at making my bins, sort of a maximum, and the sort of amount of space I want between my bins. So I chose here a quarter. So I'm making, again, this is my sample. So this is 1,000 samples. I'm going to start at -3, go up to 3. My bins are going to be 0.25. And I am now, so that's one change I made. I'm making 2 changes here. The other change I'm making here is that I am introducing a new argument, and it is going to have effect on the height. And so we're saying here that we're going to make a probability histogram rather than a frequency histogram. So we're not going to say that it occurred 100 times. We're going to say that it occurred with a probability. So we're going to be dividing by the number of samples and turning it into a probability. So that's a standard thing one might want to do with the histogram. So they have that, an argument controlling that. And that would be, so there was the sample, is the first argument. This B spec is the second argument. And then if there's this third unnamed argument, it's controlling exactly sort of like what kind of histogram. And the default histogram is a frequency histogram. How many times did something occur? But I can force it into a probability histogram. What's the likelihood that something is going to, that you're going to fall in one of those bins? And I made it light green. Okay. So this is, so we're making 2 changes here. I am not just saying how many bins I want, or automatic, figure out the bins automatically, or here's how many I want, but I'm more specifically controlling it. Here's where I want you to start. Here's where I want you to stop. Here's the division I want between them. And the other one, the probability. So turned, instead of frequencies, probabilities. Okay. And now I want to show that this, here's the, so next I want to do the same, but for 500. And when we move into this probability version, what we're going to see is that those heights now won't depend on the I'm going to make this one for the 500 samples and the one for 1,000 samples, both of the probability version, and put them together. And we're just going to see that they're going to be more similar than the frequency version. So here is my green was my sample, which was 1,000. My yellow down here, same B spec, same probability, but my smaller sample of 500. And now let's put them together. And they are now sort of the same heights. So that if you work with probability, the height now being a probability rather than a frequency sort of gives you some independence from the number of samples. So it's less affected by the number of samples because it's a probability rather than a frequency. Now what I'm going to do is take my sample, which is, again, my 1,000 sample, and I'm going to change the distance between my bins. So I'm still going to go from -3 to 3, but now my bins are an eighth rather than a quarter. And I want to see what effect that has. So I've entered that. Did I? Yes. And now I want to, so hprob was this, hprob is 1,000 samples with a quarter. The bins are the width of a quarter. And now I've made another one, the same distribution, but the bins are an eighth. And let's put them together. And so this is the same sample, and its probability. So you got the probability still depends on well, it doesn't depend on the number of samples. We saw that when comparing the 1,000 sample to the 500 sample, but the heights are dependent on the width. So if I have a smaller width, there's still more probability of to be in this smaller division. There's less probability. So these are sort of roughly sort of half the height. Or this one uh, this one bar is sort of divided into two bars. Okay. And so now there is another way called the PDF, the probability distribution function version of a histogram. And it is going to be sort of scaled uh, so that it is independent of the sample. So like the probability, it'll be independent of the sort of number of samples. So the height's not going to change. But when we change the width between the bins, that's also not going to change. So it's sort of scaled in these sort of both vertically and horizontally. And this is the version that gets us closest to like sort of what you would do in a mathematical function, which we'll see. So now I'm making a histogram. My sample is 1,000 samples from the standard normal distribution. I'm using this kind of B spec where I'm going from -3 to 3 I'm back to quarters, but now I'm doing the PDF version. Okay, so I'm going to enter that. So here is my histogram of a PDF version, probability distribution function version of a histogram. And what this version gives you is some independence from the bin size. So now I'm going to make the same thing, HPDF2 down below. Same sample, same minimum, same maximum, but I'm going to decrease the bin. So the bin was a quarter, now it's an eighth. And I changed the color, so just for comparison's sake. And then I'm going to put that green and that red together. And you can see that they're very similar. So this PDF version of the distribution of the histogram is less dependent on the width. It has the sort of the heights have gained some independence from the width of the bins that you've chosen. Okay, and then this gets us closer to PDF is sort of what you would play with in mathematics. So this is getting us close to a mathematical function. So here I'm going to take the PDF, and this is going to be not random samples, but a sort of almost sort of go to the number of samples being infinite, if you will. But I'm going to take the PDF of the normal distribution, again, standard mean of 0, standard deviation of 1. I'm going to turn that distribution into a probability distribution function as a function of x, and then plot x. Should go from minus 3 to 3 to be completely consistent here. And I'm calling that Gauss. One of the names people give to this probability distribution is the Gaussian function. And so then there is, and this is like a mathematical function. And it's a known mathematical function, so we could sort of enter it for ourselves. Depends on the exponential and x squared and so on. I will show you that in a minute. But if I put them together, the probability distribution, PDF version of the histogram, and this probability distribution, this mathematics, then that is the sort of correct comparison. So that's the histogram with the correct form to sort of compare it to math. And there we go. So we see that mathematical curve, that bell curve, that Gaussian curve, and the histogram sort of are in agreement. And you expect some deviations here and there because it's random. If the number of samples goes higher, then that should get sort of closer. The deviations would decrease there. Okay. So this function, where do I have this function? Here's where I have this function. So here is this normal or Gaussian distribution. And so here's its mathematical form. And we had a mean, this mu of 0, and the standard deviation, the sigma of 1. And I just want to look at it at the center. So mu was 0 and the x is 0. So this whole exponential part is just 1. E to 0 is 1. And the sigma was a 1. So basically it's at that point, it's 1 on 2 pi. So I just want to convince you that this is sort of that mathematical function. So I just want to get 2 times pi, and then raise that to get the square root of that and take the reciprocal of that. And here's like almost 0.4. And that's here, both the histogram and this Gaussian curve are at sort of 0.4. So that's at least some suggestion that it is indeed that function that I just showed you. Okay. Before I leave you, I want to show you sort of one more variation that, and it's not, I'm not showing you, I'm not being exhaustive. There are another important thing mathematically is what's called the cumulative distribution function, where the probabilities start off at 0 and go up to, you're summing the probabilities, so they sum up to 1. That's a sort of a standard important distribution sort of mathematically, and that is built into Wolfram Mathematica. And I'm not showing you that, but I do want to show you one other variation on the B spec that can be useful. So I'm making a new distribution here. It's a sort of a quick fake IQ. So IQs are presumably have a mean of 100 and a standard deviation of 15. So I did normal 100, 15. And then I said I wanted 500 of them. And then I got the integer part. So I didn't want any crazy fractions hanging around. So this is just new data. And then just because I want to motivate this other version of the B spec, of the bin spec. And so what you can make is a histogram of the data, IQs. And if you have curly, sort of, I don't know, a list of lists, but only one list in the only one inner list in the outer list, but then these are sort of the lower edge of bins. So I said I wanted one huge bin spread from 0 to 70. So these little like that look like divisions down here, they're not divisions. They are just tick marks from my axes. This is just one very spread out bin. So I have a bin that goes from 0 to 70, not including 70. And then I have something from 70 to 79. I have integers, so I can say that 79 or just shy of 80. I go from 80 to 90. I include 80, not include 90. And then here's the one reason for this version here is this so-called normal intelligence, if you believe in all that, then that sort of normal division you usually make like broader than the other ones. So you have sort of so there we're going from 90 to 110. And so that's what this version gives you. What I had up above, the bins were sort of normal or had the same width, but I can, if you want for any reason, and if you sort of look up Wikipedia sort of things on IQ, they normally sort of when they're categorizing them, that middle category is expanded compared to the other ones. The other ones seem to span about, well, this bottom one's very large, about 70, then it's sort of 10, 10, 20, 10, 10. And so there we have. So you can control these. And you can have this sort of someplace else and then have what's called the name B spec. But I just wanted to sort of more hard code it right in here, just show you just another version of B spec. There are other versions, as I said, there was the standard was for that third argument in the histogram. The default was frequencies. You could do probabilities. You could do probability distribution function. You could do cumulative probability distribution function, and I think there might have been one or two other things. But I just wanted to show you. Let me just run this one to show you that it is indeed what it looks like. They're just variations on all of these things, but I wanted to show you a few of them that are available in Wolfram or Wolfram-Cloud or Mathematica, sort of variations on the histogram. And the one that became sort of most interesting, if you want to sort of compare your distribution to some mathematics, is the PDF version. Thanks for your attention.